Welcome to the GLOBECOM 2021 tutorial entitled Intelligent Reflecting Surfaces for Wireless Communications, Fundamentals, Designs, and Open Issues. And I'm Emil Björnson. I'm a professor at KTH in Sweden, and I will give the first part of this tutorial, and then the second part will be given by Rui Chang from the National University of Singapore. Looking at the outline of part 1, I will first provide you with an introduction to intelligent reflecting surfaces, what it is and what it means to do active beamforming and passive beamforming. And then I will talk about system modeling and some of the basic optimization that you can do with these surfaces. So I will derive a system model and I will optimize the IRS configuration. Then I will go more in detail into how to model the channels when we are operating over a narrowband system channel. And I will particularly talk about the path loss, array responses, and spatial correlation. Then I will talk about channel estimation for narrowband channels and move over to wideband channels and see what changes there in terms of the optimization. And I will wrap up part 1 by talking about competing technologies and some of the potential weaknesses with the IRS, focusing on what is the best situation to utilize IRS. And some of my research funding agencies are the Swedish Foundation for Strategic Research and the Swedish Research Council, so they are sponsoring my research in this area. So let me start now with the introduction. So we are seeing a wireless technology that is evolving over time, and it's typically happening in generations, but also in between generations a lot of changes are happening in smaller releases. So if you look back at 4G, this is a situation that is typical. You have a sector antenna that is transmitting signals towards users. So it has a directive beam towards the earth, where the people are, and into a sector of maybe 120 degrees. So we place it on the rooftop or at some other elevated location. And if you are a fortunate user that is standing in front of the base station, since this sector antenna is focusing the signal down to the ground into the sector, you will get a stronger signal, maybe 15-18 decibel stronger signal than you will get if this antenna were just radiating the signals in all directions uniformly. However, there will always be some users that are falling into your sector, your coverage area, that are not in the side of this main beam. I call these the unfortunate users because the signal that could reach this user would have to bounce off this building. And then even in that case, probably it won't bend off towards this user, but there will at least be some signals behind this. But the shadowing effect here is something that we are experiencing every day when we feel that we are not having a good coverage, even if we are relatively close to a base station. So how can we deal with this type of situations? Well, 5G is changing the type of base station that we're using. So instead of having a fixed beam, we have this antenna arrays that is called massive MIMO, where we are considering many low-gain antennas that can cooperate in order to form beams that are directive in different directions, instead of having just one fixed beam as before. So we can use it to both serve this fortunate user and this unfortunate user at the same time. And in particular, then when we want to serve this user, we can form a beam towards this building here so it then is reflected or scattered around the corner and reaches this user. It's not ideal, but we get the strongest signal at that location or at any other location in the cell than you would get with a fixed beam antenna. What could we then do in the future to improve the situation even more? Well, one option would be that we could do something with this reflection here. What if we can control objects in the propagation environment to help them carry the signal towards the desired location of the users? In this case here, could we rotate the building? Probably not. But maybe we can put up some objects on the building facades that is controlling how they're reflecting the signals. Because conventionally, well, if the signal comes in with a certain angle and the surface is flat, it will be going out with the same angle but in the opposite direction, according to Snell's law. Or if the surface is rough, it will scatter the signal in many directions, but that will also lead to a weak signal at this location because the signal energy is really dispersed. So what could we potentially do at this location in 6G? Well, we can deploy what is known as a reconfigurable meta-surface. That is a material that can change its properties over time. And in particular, when we are using it in order to control propagation in wireless communications like I'm illustrating here, we can call it an intelligent reflecting surface, or IRS, as we do in this tutorial. It's also known as reconfigurable intelligent surface, or RIS, and that terminology basically means the same thing. So, in order to understand how such an intelligent reflecting surface could behave, let us first look at how the beamforming from a massive MIMO or multi-antenna array works. So, when we do beamforming, we are achieving directivity by constructive interference of waves emitted from multiple locations. So let's start by looking at these two antennas here. They are radiating the same signals at the same time. So the green waves here are radiating at the same time, the gray at the same time, the orange at the same time, and so on. And as you can see, there are certain directions where these signals seem to be pointing in the same direction. So where we will reach the signals to from these two antennas at the same time. You see that they're intersecting here and here and here, so that is sort of saying that if we are moving upwards here, the signal that comes from the two different antennas will probably be reached in phase. So if we are observing signals over here, you will basically get constructive interference, while in other directions you won't. More in detail, both of these antennas now are assumed to radiate the signal uniformly in all directions, but they're transmitting the same signal at the same time. So if you start to measure the strength of the signal in different angular directions, it will look more like this. That you get a strong signal upwards here when you see the constructive interference, and then a weaker and weaker signal, and towards the edges the signals from these two antennas will cancel out each other and you will get barely nothing. So even if you have two antennas that have no preferred directivity here, together when we are transmitting the same signal, we get a preferred directivity. So could we then control in which direction this directivity happens? Yes, we can. If we have these two antennas again, but now we let the right antenna transmit with a slight delay, then this is what will happen. The signal that have left the right antenna will have not propagate as far. So the green one are intersecting here, the gray here, the orange here, and so on. And this is sort of illustrating that it is in this direction that you will see the constructive interference. So once again, we are transmitting the same signal from both the antennas, but with a small delay. And that means that when we start to measure the strength of the signal at different angular directions, this is what we will see. That we have a strong beam in one direction, and then in another direction it will be substantially weaker. So we can create directivity by constructive interference of signals transmitted from different locations, if we are controlling their delays. So how would that then work if we are considering materials that are reflecting signals? Well, suppose a plane wave is moving like this towards a surface. And then let's take the surface and divide into small segments, points like this. Then there is something called the Huygens-Fresnel principle that says that we can view the reflected signal from this surface as being the superposition of signals transmitted from these different points. So every point scatters a spherical wave, and constructive interference between the scattered waves from these different points here along the entire surface will determine the directivity. So since the signal is reaching this point first, its reflected signals, these waves here, will have reached further away before the signal from here is being reflected. We have these two waves here, and then this one had not reached that far. But the blue curve here that is representing a signal that have traveled equally far, you can see that it is in this direction here where we will have a strong signal. The constructive interference will happen downwards here. So if we have an infinite-sized homogeneous surface, like a ground plane, then a plane wave that comes in will result in a plane wave that goes out. And actually, the angle of the signal here coming in with respect to the normal is determining the angle of the signal that goes out again. What will then happen if the surface is not infinitely large? Well, in that case, you will still use the same principle. You divide the surface into small elements, each of them are re-rated in signal, with the delay determined by how far the wave have reached before it hits the surface. And then the signal will in this case be beamformed. It will be like we are transmitting with different delays from these different segments of the surface. And we get the beamforming downwards here. It's not a plane wave anymore, but it has a main directivity. And the beam width will be inversely proportional to the width of the surface. That is something that always happens when we are transmitting from an array. And then of course when the surface becomes infinitely large, you have a beam width that goes to 0 and you get a plane wave. So this is how we can interpret stuff like this. And this happens with all kinds of materials around us, but can we change what is going on within the materials in addition to this? Well, I've stressed here that these are homogeneous surfaces, so they have the same properties everywhere. But what if we have a heterogeneous surface that is behaving differently in different parts of itself? This is what we are utilizing when we work with an IRS. We are purposely creating a heterogeneous surface that can passively beamform signals. So suppose we have a transmitter here, transmit the signal, it is impinging on this surface. The colors here are representing different impedance values over the surface that are creating different additional phase shifts or delay of the signals before they get re-radiated. Then we can control this pattern here somehow, if we can do it, so that the signal will create constructed interference in a particular direction. And in this case, we would like to do it towards user 1 here. Then at the next moment, we are changing the controller here so that we get a different phase shift or impedance pattern over the surface. And all of a sudden, we are reflecting the signal as a beam in another direction towards user 2 here. And this is something that we can switch with over time, back and forth depending on which user we are actually serving for the moment. And how does it work? Well, the surface is containing small elements here. We typically want them to be sub-wavelength sized, smaller than a conventional antenna even, because we would like them to scatter the signal in all directions almost uniformly, as they will do when they're very small. And then each element is a passive patch that is just reflecting the signal, but we can change some properties using a switch, such as a diode. Change things like the impedance of the elements, which is then changing the reflection coefficient, which is determine the amplitude and the phase shift of the signal before it gets re-radiated. So it is the scattering of many elements here that are changing. So on the microscopic level, each element here is just a stupid patch that is re-radiating the signal with no controllability except for a phase shift. But the controlled phase shift pattern over the entire surface is creating the directivity. So let us then go into the geometrical interpretation at the level of the entire surface at the global level. So we looked before at this normal reflection. The signal goes in from one direction, it goes out with the same directivity but on the other side of the normal. If this is the user that is supposed to receive the signal, then it's problematic that the wave is actually not reaching it. What can we do? Well, we could take this say metal sheet and bend it like this. If you bend it in the right way and you then apply the Hagen-Fresnel principle, you will see that the signal that are re-radiated by the different parts here of the surface will create construct interference at a particular point or in a particular direction. In this case, it's here at the user. And what I have utilized here is essentially the same principle as for a satellite receiver, which is a parabolic surface that collects the signals and then it's reflecting them towards a feeder. So what we are then doing is that we bend the surface, but that is not very convenient to do. You can't bend a building, for example, just to reflect the signal towards a particular user location. So what an IRS can do instead is to be a flat surface, but change the properties of the surface, turn it into a heterogeneous surface, create additional phase shifts that delays the signal so that it behaves as if it's bended, even if it's not. So we synthesize a different shape of the surface. And by doing this, we can beamform in the sense of beamforming towards a point that is close by or in a direction which is essentially the same thing as beamforming towards a point that is infinitely far away in a particular direction. And different phase shift patterns will result in these different things. So what can we use such a capability for? Well, there is a variety of different prospective use cases here. And here is a figure from this recent tutorial, which is demonstrating some of them. So we could have a transmitter here that is sending out the signals, and in order to help a user to localize itself, when it can't be reached by a satellite, it will get the signal from the transmitter, and it will get from reflected points that are at fixed locations, and that will help with localization. We can have users that are at the edge of the cell, and therefore they might be blocked, and we can help them to get more signal power by putting up these surfaces on buildings and get them stronger signal where they are. And you can help from multiple base stations, for example. You might have a user at a location that gets the signal from the air. You might have an IRS that is reflecting the signal from the sky, or that is reflecting the signal around corners to help out with dead zones. And you can imagine many other scenarios here. You can use the surface to beamform energy and information at the same time, like in the simultaneous wireless information and power transfer. You can have smart offices that are providing good coverage everywhere, and physical layer security can be used to, say, you transmit to one user and one car here, but you at the same time are making sure that the signals that are reflected at certain locations here, make sure that you are cancelling out the signal at undesired locations where an eavesdropper might be. So there is really a variety of different prospective use cases here, and I will not focus particularly on these use cases in the rest of my part, but instead go into how it works in the basic scenario where we would like to help out a cell edge user, someone who might be blocked from the base station. And to do that, I will develop a system model, and then I will use it to optimize the IRS configuration in order to maximize the performance for a user. We will use basic signals and systems theory in order to analyze an IRS-aided communication system. So in signals and systems, a signal can be an input to a system, which is a filter or box that is outputting an output signal. And I have PP as passband as the subscripts here, because I'm considering signals that are centered around some carrier frequency, FC, and have a bandwidth B. And the transmitted signal here, X, have a particular shape, and then the received signal is confined to the same part of the frequency domain, but it will be attenuated because of the wireless signal, and then we will typically also have a different shape due to behaviors over the communication channel. And how do we describe it? Well, we can describe how we get from the input to the output using the impulse response. If we have a linear time invariant system, which wireless channels can be described as if we have a short amount of time where everything in the propagation environment is constant. Then an impulse response is a function. We take the convolution between the input and the impulse response to get the output. And this integral is a description of that as well. So how can a communication channel look like with a system filter? Well, you transmit the signal from an antenna, and when you receive it over here, you are then getting different copies of it. The signal might bounce off this building, it might go directly, and it might bounce off this vehicle here. The direct path, we will have a particular delay and a particular attenuation here. The reflected path here will have another attenuation and another delay, and this path will have yet another delay and attenuation. We can now get the impulse response by letting the transmitted signal be a direct delta impulse. In that case, we are getting the same 3 different attenuations here, and then we get delta functions with the 3 different delays. And in general, this is how a communication channel looks like. We might have many different paths of this kind. There might even be a continuum of them, but it is this way of describing a communication channel. So the transmitted and received signals are in a passband around the carrier frequency with a particular bandwidth. But all the communication theory that exists are basically generated for the complex baseband, where we are moving these signals down to be centered around the 0 frequency. So we will not have theory that is sort of focused only on one carrier frequency. So if we downshift everything to be centered around the 0 frequency, now two interesting things happens. One is that this bandwidth of B shrinks to B over 2 because it only goes from minus B over 2 to plus B over 2. That might seem like we are cutting the bandwidth somehow, but the difference is that this signal is real valued while this is complex valued because we are not having symmetry around the origin. So actually half of the bandwidth is just hidden in the complex part instead. So the complex baseband representation is then very useful when studying communication systems, and we would like to then take our descriptions of the system and inputs and shift it down to the complex baseband as well. So shifting the frequency domain components here is just to utilize these two properties. We are taking the this part that is showing up on the positive frequencies and we shift it down by removing FC from it, and we do the same thing with the received signal. And then since there is also a component on negative frequencies, there is a component that is shifting it as well to the origin, and the same thing for the received signal, and then we divide by square root of 2 to keep the energy constant. And if you would like to do the same thing with the entire filter, well then we take the signals that we are getting from these things that are in the complex baseband now, so the time domain version of these ones. We send into a filter, we get the output, which is this complex baseband output. And how do we obtain the output? Well, we take the input, we take a convolution with some kind of impulse response that is representing it. And the way to obtain that one is that we just take the impulse response that we would have in the passband, and we are downshifting it. So we multiply it to e to the power minus j2 pi fct. And that is the only difference. Apart from that, we can use the same theory. So how can we then analyze a system that contains an intelligent reflecting surface? For example, we have a transmitter that sends a signal. We have an IRS with n elements that are re-radiating that signal towards the receiver. And there might also be a direct path. Well, now we have a collection of different systems. We have a direct channel or uncontrollable channel. So if this is a transmitted signal, then the received signal will contain one component that is not involved in the IRS. So there is an impulse response describing that one. Then, for each of these n elements here, we can study them individually. There will be a channel to the element, described by some kind of impulse response. Then there will be some filtering going on within the surface before it is re-radiated. And then there will be a wireless channel from that element to the receiver. So we have 3 different impulse responses like this. And if we convolve all 3 with each other, then you will get the components and the impulse response through element 1. Then we do the same thing from element 2. The only thing here that is different is the index here, 2, 2. And then we go down to element n and we continue like that. So the received signal is the combination of n plus 1 paths. One that goes without IRS and n paths that is involving the n different elements. And what is important here is that everything is constant except for what is going on within the elements here. So these impulse responses that is involving the IRS elements, they can be controlled. That's why there is a subscript here, theta I, theta 1, theta 2, theta n. So these are our control variables. We can change the impulse responses in different ways. And the end-to-end impulse response will be what we are getting when we are adding up the impulse response for a direct channel, and we are summing up over all our elements. We take the convolution between the impulse response to the surface, within the surface, and from the surface. And this is then the description. And you can model all of these channels in the same way as we are conventionally modeling communication channels, and we will return to that later as well. The important difference is what is happening inside an element, and that we will have a closer look at now. So here is a prototype of an iris containing 22 rows and 55 columns here. So there is more than 1,000 elements, and these are designed for the 5.8 GHz band, which is a Wi-Fi band. So what is happening within each element? Well, each element is a patch with a particular bias voltage that we can control. And in this case, there is some dielectric substrate, some vector diodes that can be changed, and you can find the detail in this recent paper by me. And what is important is that there is a reflection coefficient that is describing this element and what happens with the amplitude and the phase before the signal gets radiated. And since we can change a bias voltage over the surface, we can change the reflection coefficients. The reflection coefficient is computed as the impedance of the element, which is affected by the bias voltage, minus the impedance of the surrounding air, divided by the impedance of the surface plus the impedance of the surrounding air. And this is a complex number in general, and if we are considering the amplitude and the phase of it, well, then we can look at its frequency dependency. And here we are showing what happens with amplitudes and with the phases. So let's start with the amplitudes. We can assign different bias voltages, resulting in curves of different kinds here. And depending on which we are choosing, from 0 up to 19 volts here, there are different curves. But within the 5.8 GHz band, and particularly 20 MHz carrier that we were considering in this paper, yes, there are some variations here. In particular, if you use linear scale here, there are variations that you can notice, but they're rather small. In dB scale, this is like 1 decibel or something like that. So from a wireless communication perspective, these variations are essentially negligible. The important variations is, however, the phase response, which is changing with frequency, but within the 20 MHz band, for each curve here, we have essentially constant value. But it is different depending on what bias voltage we are using. So we might be starting here at 0 volt with, I don't know, minus 110 degrees. And then we are increasing the bias voltage, and we're jumping upwards along the axis here in the phases, and we reach up to, say, 120 degrees, plus 120 degrees. So we can vary the phase a lot, depending on what bias voltage we're having. And that is the important thing. We can determine the phase shift of the re-radiated signal, and we can do that at an element by element level. So the important thing then is that we have a roughly constant value within the band we're interested in. I will neglect the amplitude variations in the rest of my part here, and you will see, however, that we can change the phase shifts in a variety of manner. Either it might be a continuous change, if we can change the voltage continuously, or we might have a few different options to choose between if we can only have some discrete values of this voltage. We will now consider a narrowband system model, where the channel from transmitter to the surface and from the surface to the receiver, each such channel is only described by a complex scalar. So we have A1 from the transmitter to element 1, A2 to element 2, and AN for element N. So there are N elements in total in this IRS. And from each element, there is also a channel to the receiver, B1, B2, Bn. And then the interesting thing is what happens within the surface. We have a phase shift that we can control, described by this vector, omega theta, and it's e to the power of minus j, theta 1, theta 2, and then theta n. So these are the different phase shifts. So what will then happen at the receiver? Well, we have 3 different impulse responses. Each of them is essentially a delta function multiplied with these corresponding different constants here. So the end-to-end channel can be described like this. We have a summation over all of the elements. We get A of n from element n, B of n from element n to the receiver, and then we have the phase shift for element n, like this. And since we have a summation over multiplication of 3 terms here, all of them coming from vectors, we can describe this using the vectors as well. And a convenient way of doing that is to take A and B and multiply them together element-wise to form a new vector with A1 times B1, A2 times B2, and so on. And then take an inner product with this omega vector, like this. And then we form this summation. And I will call this end-to-end channel coefficient gamma. The goal is to maximize gamma in absolute value square, because if we can make that coefficient as large as possible, we will also have a high signal-to-noise ratio. Okay, so how should we do that? Well, we have a vector here, we have a vector here. And we can also view it as a summation over these terms here. And if we add up positive numbers and negative numbers, they will cancel out each other. And in the same way, when we add up complex numbers, if they have faces that are pointing in opposite directions, they will cancel out each other. But if all the faces are the same, then we will add on top of each other. And that is what we would like to have in order to make them as large as possible. So we should make sure that we have faces in A times B and in omega here that are opposite, so they are cancelling out each other. So if we take for element n, which has a face, which is the argument of an times bn, and we assign that at theta n, and then since we have a minus sign here, they will cancel out each other. So all of these terms here will generate a positive real value number. In that case, the absolute value square of gamma, which is this term here, will be getting its largest number, which is to sum up only the absolute values of each of the different terms, and then we square it. Another way of writing this is to take the element-wise product between two vectors, take the one norm, which is what we get when we take the absolute values, and then square that entire thing. That is the maximum SNR that we can get. So this is how we are selecting the best IRS configuration in a narrowband case with a single antenna at the transmitter and at the receiver. If we now add a direct path, what will happen? A path that goes directly between the transmitter and the receiver without involving the IRS. Well, in our expression, we should then add a complex scalar. Let's call it HD here to gamma. And we have HD added here. And what should we do then? Well, we still would like all of these terms here to have the same phase. So we can reach an upper bound where we're just summing up the absolute values of all of the terms here. And previously we were making sure that all of the terms in this summation had the same phase. But we actually didn't tune what phase it would have. I said it was going to be positive real valued, but that was not necessary. We can instead make sure that all of the terms in this sum here have the same phase as HD. So in that way, we are removing first the phase that an times bn has, and then we are adding the phase that HD has, like this. In that way, we achieve this upper bound where we once again are just considering the absolute values of all the terms because they are always adding on top of each other. What will then happen with the power when we are considering the signals like this? Well, to get more insight into this, instead of having a lot of different terms here, let's simplify. Let's say that an is equal to one absolute value square root of some parameter called alpha. And the absolute value of bn is beta with the square root on it. And the absolute value of HD, I will call it square root of rho. Then, what I have here, absolute value of HD is just the square root of rho. And here I have n terms, and all of them will now have the same value. So we have an n, and then we have square root of alpha, square root of beta, like this. And I have an absolute value square. If I am expanding this square, I will get this term squared, so n squared alpha beta. I will get this term squared, rho. And then I will get 2n square root of alpha beta rho. Okay, what happens with this term? Well, it depends really on which terms that are dominant. If this term, the one that involves the IRS, is the dominant term, well then we can neglect the two last terms here, and we have something that looks like n square alpha beta. And this is called the squaring law. When we have enough number of elements, this SNR, or this is the SNR proportional to this factor here, it will grow with the number of elements squared. So that is happening when the direct path is small. But if the direct path is much stronger than the reflected paths, well then we can neglect the reflected path instead. We only get rho here, and then it doesn't really matter how many elements we have because they are not really adding anything to our link budget. The SNR is roughly the same. But the interesting case is, of course, when the IRS is actually making difference, when the SNR becomes proportional to the number of elements squared. Why does it become a square here? Well, this is what I'm trying to explain now. So we have a transmitter that is sending a signal, towards the IRS. And since the surface area here, the IRS, is proportional to the number of elements, we get an aperture gain. We collect energy proportional to its area. So that is where we get one of these n terms. Then we let the surface beamform the signal in a passive manner towards the receiver. And the larger the surface is, the more directive this beam is going to be. And that's why we get the beamforming gain that is proportional to the number of elements. And then n by n becomes n squared. So that's why the SNR is growing like n squared. So we have a beamforming gain that is only then for the desired signal. And we have an aperture gain here that applies to any signal that is reaching this one, and noise and whatever interfering signals. So if there are other interfering signals or noisy signals around, then we need to be careful with the aperture gain here. But the beamforming gain will always be useful, and we will come back to these things again. Okay, so we were considering phase shifts, and we were finding the phase shifts that are maximizing the SNR. But it's not necessary that we can choose that value in practice, depending on if we can select the phase shifts exactly to any number, or if we are limited to a certain number of states, like in this example where there was different bias voltages. So to look a bit deeper into what happens when we have only a finite resolution on the phase shift, I have some examples here. So in this case, I can only select phase shifts that are either 0 or pi. And I only have two elements for simplicity. So I have a direct path, then I have A1, B1 and the phase shift, plus A2, B2 and the phase shift. And if I skip this phase shift for the moment, these are different points on the unit circle. I've neglected sort of the amplitude variation that might be there for simplicity. So we have these different points. And what can we do with our phase shift? Well, we can take the red and the green points and move them along the unit circle with these phase shifts, while the blue one can't be moved because it's direct path. So if we only have these two options, if we select the phase shift as 0, the red and green will stand or remain at the point where they already are. While if we select pi, they will move to the opposite side. So the red one can move here with the phase shift of pi, and the green one can move here with the phase shift of pi. And the good thing when we have two phase shifts is we can always move the signals so that they are in the same half space as the direct path. So we can gather all the terms in the same half space, which means that we will not have both the real and imaginary part cancelling out each other. There could be signals here opposite of each other that will have some things that cancel out, but they will be rather close to each other, so they will never cancel out each other perfectly. If we are increasing and have now 4 different phase shifts, minus pi over 2, 0, pi over 2, and plus pi, then we can move the red and the green points not only to one opposite location, but there will be one location in each quadrant of the unit circle where it could appear. And what can we do? Well, we would like it to gather them in the same quadrant at HD here. And the red one, we already know how to move it. It was the case that we had over here. But the green one, we can now move it to this point by shifting it only by pi over 2. And now all of the signals are gathered in the same quadrant as the direct path here. And that will help out the signals to add up constructively. So this is the important thing here, that since we would like them to have roughly the same phases, we don't need a very high resolution on our phase shifting to achieve that. Let me demonstrate this in a basic performance comparison. I have a transmitter that transmits to a receiver. I have an IRS, and the path to the IRS is minus 80 dB as path loss. I have minus 60 dB as path loss between the IRS to the receiver, and then I will compare two different direct paths. Either a weak one with minus 110 dB, or a not weak but not super strong either, rho is equal to minus 80 dB, so it's equal to this path strength here. And I have some assumption around bandwidth and transmit powers. These are not exactly the most important thing you can find in this paper. Instead, let's focus on the capacity in megabits per second that we can deliver over this bandwidth. And I'm changing the number of IRS elements from 0 up to 200. And what we can see is in case 1, when we have a weak direct path, then increasing the number of elements quickly leads to an improvement in capacity, and we are getting a many times higher capacity than at the starting point here, where we almost have 0 megabit per second. And the upper curve here is when we can select the ideal phase shifts. If we only have 4 configurations, we can move all of them into the same quadrant. We are losing a little bit, but it's not much. If we have a strong, or not semi-strong, direct path in case 2 here, then what we can see is that we already start at a rather high capacity value, and we see an improvement with the number of elements, but now we are not really seeing the n-square improvement because the direct path is rather strong. And we also see that the benefit of having ideal configuration over 4 configurations is rather small as well, because a lot of the power goes over a direct path. So the IRS is particularly helpful when the direct path is relatively weak, as in case 1. That is cases where we should target using this technology. What will happen asymptotically then? If the SNR grows with n square, will that go on forever? Not really. So here I'm standing in front of a surface where I have a small IRS here on the wall. And if I'm in the far field, this element here will sort of scatter the signal. And I'm 2.5 meters from the surface, and then I have 25 meters to transmitter. And we are considering here the total channel gain to the receiver here when we are changing the number of elements. And if we have a relatively small number of elements here, then we can view the transmitter here as a directive scatterer. So it forms a beam towards the receiver, but it's not a perfect laser sharp thing. And all the elements in the surface will contribute equally. And since we don't have any strong direct path in this case here, the SNR will grow proportional to n square. But then, when we get more and more elements, I'm showing 3 different curves here. And what are these curves? Well, I have the red curve here is a far field approximation, so I'm considering that n square will go on forever. Then I have an exact curve where we are computing exactly what happens when we are close, and then we have one case when we let the surface focus at the point that is in the same direction but infinitely far away, which means that it will, when we increase the size, it will try to behave as a mirror. And when we are reaching a point where we are in the radiative near field of the surface, so its size becomes comparable to this distance from the surface where I am, then the signal will not really scatter it anymore, but it will focus the signal precisely onto the point where the receiver is. And in this case, we are getting the black curve here. And we are seeing a convergence towards receiving most of the power, but not everything. And the far field approximation will break down eventually at that point, because now all the elements are not contributing as much anymore. So this n square gain is disappearing eventually. But in most practical cases, we will see an n square SNR behavior. And there will be an asymptotic limit where we receive almost all the power. The important thing here is to remember that we should never really view the surface as a mirror, because either it is small enough to behave as a mirror, more like a scatter, or when it's large, we don't want to convert to this number here that we will get if it behaves as a mirror, because a mirror is reflecting a plane wave as a plane wave. We would like to focus signal at the receiver and do much better, and that is what this asymptotic limit is describing. Let's now take a closer look at channel modeling for narrowband channels. So suppose we have a transmit antenna here at a distance d from the elements, and the IRS contains n elements, each of them have an area A. How do we model the path loss in a situation like that? Well, the path loss when we are transmitting from an isotropic antenna is to take the effective area of the antenna that we are receiving with, in this case the element size here, and we divide by 4 pi d square, where d is the propagation distance. This is in line of sight, of course. And this is because a sphere with radius d has this surface area. So the effective area divided by the total surface area is describing how much energy it collects. And if each of the elements are sub-lambda sized, where lambda is the wavelength, well, then the effective area is essentially equal to the area of the antenna, which might be lambda over 5 squared. And in that case, we can replace the effective area with the actual physical area of the element, like this. This is a basic way of computing the path loss in line of sight. What we should remember is that the elements that we have in our surface are typically not isotropic receive antennas. So if we would like to relate this path loss to what we get with an isotropic antenna, which is something that you might find in tables describing different path loss models, then we should take the area and divide it with the area of a isotropic antenna, lambda squared over 4 pi. So this factor here is smaller than 1 typically. So for example, if you would like to use the 3DPP urban microcell model, it is described for isotropic transmit and receive antennas like this. The isotropic path loss in dB is minus 37.5 dB minus 22 log 10 of the distance divided by 1 meter. And this is for isotropic antennas. If the transmit antenna is isotropic, but the element have a particular area A, we should take this term that we have for the isotropic antennas, and then we should add an extra term here, 10 times log 10 of this fraction here that is describing how much smaller our elements are compared to an isotropic antenna. And this is typically a negative number because this is smaller than 1. So we can use all of the different path loss models that you find in literature as long as we are compensating for the receive antenna or the element sizes here. Okay, so we can apply that both when we are receiving things at ARS and when we are transmitting it. But what is also important is to consider what happens when we are relating different elements to each other, because the signals will come from different directions and leave in particular directions. So if you're considering signal that comes from the far field or is leaving in the far field, they will essentially be like plane waves that comes in with a particular azimuth angle. So here I'm showing the IRS in the YZ plane, and I'm defining the azimuth angle as being 0 when we have the broadside direction from it, and then we can vary it between minus pi over 2 and plus pi over 2 in different directions like this. And then we have the elevation angle, which is 0 right in front of the surface, and then it can go upwards and downwards from minus pi over 2 to pi over 2. Notice that some people are using the zenith angle instead, which goes from 0 to pi, but I think the elevation angle like this makes more practical sense because then 0 is the angle that goes perpendicularly to the surface. So consider an element here at location UN in 3 dimensions, and it is in the YZ plane. Well, then if a signal comes in with one of these different, or with the combination of azimuth and elevation angles, we can determine the phase shift at each point here on the surface and relate them to each other, because that is important. It's the same wave from that angle that reaches all the different elements. And we can define what is known as the array response vector, which describes the relative phase shifts over the different elements with respect to an antenna in or element in the origin. The way of doing that is to write up R, which is a function of two angles, and it contains e to the power of j, and then we have an inner product between the location of an element and something that we call the wave vector, which is 2 pi divided by lambda. So this has to do with the phase shifts. And then this cosine theta, cosine phi, cosine theta, sine phi, and sine of theta. This is describing the location on the unit sphere in the particular angular direction. So by taking this input here, we are determining what are the point at the unit sphere where the surface, the plane wave is first hitting, and then we are computing these computations here in order to figure out how far the signal needs to go to reach a particular point here with respect to the origin. So this array response vector will describe the phase shifts of that incoming plane wave. So if we would like to determine the channel vector A to the surface or the channel vector B from the surface, for a wave that comes in from a particular angle or leaving a particular angle, it will be a constant time this array response vector with respect to those angles. We can use this to create basic multipath channels. So say for example the wave come in from these 3 different directions, or L different directions. Then the channel vector will then be a summation over the different direction of the waves, the respective array response vectors with phi L, theta L, and then there is some coefficients here that will describe how strong the wave is from each of these different directions. And I will call it CL for cluster L or direction L here, and I will also normalize with square root of L. That is just because I will use it later to let L go to infinity. And when we are now describing this channel here, there are essentially 2 different ways of considering it. A is a vector of dimension n in a complex domain, so we have n complex parameters. But we could also describe it using this summation here. And in this summation we have L parts, and each one of them we have 2 real valued angles, and we have a complex term here. So we have 4 times L different real parameters that we can describe. And if the channel is sparse, meaning that L is a small number, or that there is only 1 or a few strong paths and the other ones are negligible, well then we could maybe get away with using a parameterization with 4L real parameters instead of n complex parameters, and describe the channel still in a very good way. This might particularly be the case in line of sight channels. Okay, so let's consider a rich multipath scenario where we have a lot of multipaths. So we have a cluster of waves coming in from one direction, and a cluster wave from another, and a cluster wave from a third direction, for example. We can describe it still in this particular way that we had before, with L-plane waves. But when we have a cluster of different signals, so L becomes large here, then this turns into a summation of many terms. Each of them might have a roughly random attenuation and phase shift, and if you sum up many terms, you like to get a Gaussian distribution, and that is why A will become approximately Rayleigh fading, so complex normal with a zero mean and a covariance matrix C. And we achieve this when L goes to infinity, number of paths goes to infinity. And the covariance matrix C is determined by the physics around us. So if we assume these CL terms here are ID random variables with zero mean because they have phase shift in them, they have a particular variance, A mu, so A describes the size of each element, and mu describes sort of the general path loss apart from the area. And we have an angle distribution as well, that is ID, or using some kind of probability density function. Then we can compute the covariance matrix C. Its nth element is A times mu, and then we should take this CL. It comes from that variance. We get CL times CL conjugate, and we are also getting the impulse. In this array response vectors, we were having terms of this kind here for element n and for element m, and when we are taking the expectation here of nm, we will get the element from n, and we'll get the element from m with the conjugate on it, and that's why we get these expectations here. So what it will be the randomness here that is left, well, it is an expectation with respect to this distribution of angles like this, while all of them have, each cluster, each component have this variance. So this is a general expression for whatever distribution we have of the multipaths from different angular directions. We can compute this, and we then have a Rayleigh fading model. If we consider isotropic scattering, which means that we have a uniform distribution of paths from all directions, from pi over 2 to minus pi over 2 in the azimuth domain, they can't come from behind, so just in a 1/2 space here, from up and down equally. Then a uniform distribution, when we are using spherical coordinates, should contain a cosine of the elevation angle, because of the fact that there are more angles, elevation angles, here than up here. And then we should divide by 2 pi in order to get the PDF that integrates up to 1. And this is the expression of it. And you can then compute the covariance matrix exactly. We do it in this paper here. We get A times mu times the sinc function of 2 divided by lambda multiplied with the distance between the two antennas that we are comparing. So the spatial correlation in the complex Gaussian or Rayleigh fading model will be determined by how close the two elements that we are considering are towards each other. Despite this, you can find many papers on this IRS topic that says that we assume IID Rayleigh fading. And the problem with this is that it doesn't really happen, particularly because IRS is characterized by having elements that are small. Element spacings, in particular like lambda over 4. Now I am considering one particular element. I have 10 by 10 elements. I am considering element 5, 5, so on row 5 and column 5. And I'm considering the correlation based on what we had before. And I normalize it so that 1 is the highest correlation. And then the element is correlated with itself. Its random realization is correlated with itself. So then we get 1 as correlation. The surrounding elements will have a rather correlated channel realization. And then it goes down and it goes down, and we can see the sinc shape here is just that the correlation is defined with an absolute value, so it doesn't fluctuate up and down. But you can see that all of the elements here have a non-negligible correlation, apart from a few locations, like this one, where we happen to be exactly at a wavelength divided by 2 distance between different terms. If we then consider that this is how the description was, we see that the sinc function is 2 divided by lambda times the distance between them. So no correlation only happens when the element is precisely half a wavelength apart. And if that happens horizontally and vertically, like I'm showing here, when I'm increasing the element spacing to lambda over 2, then we see that on the same row and at the same column as this antenna 5 on the 5th row and column, we have no correlation. Fine, lambda over 2 spacing works, but only on those rows and columns. Everywhere else there is correlation. So there will always be correlation when we are considering Rayleigh fading models with IRS, because we always have that when we have 2-dimensional arrays. That said, it doesn't change really what kind of power gains, beamforming gains we can achieve with IRS. It's more important when we are considering the channel estimation and the interference between different systems and things like that. So, to also demonstrate how spatial correlation appears naturally, let us consider a square array with isotropic scattering elements. And I'm computing the rank of the covariance matrix, and there is a theorem saying that this rank divided by pi n number of elements, a the element size, divided by lambda square approaches 1 when we have a large surface with small elements such that the total area of the surface is still large. And here is a description of what that really means. The rank is not equal to the number of elements, it's equal to this term here approximately. So if I would be having IID Rayleigh fading in a case with 1600 elements, so 40 by 40 element array, then I will have all the eigenvalues of the covariance matrix equal to 1. But if I have a lambda over 2 spacing, you see that I'm showing here the eigenvalues in order number and their values. We'll have some that are substantially larger than 1, and then we'll have some that are around 1, and then there will be some that are essentially 0 because of spatial correlation. And this round circle here is describing this value here. So if since we have a finite sized system, we have a slightly larger rank than predicted by this number. If we have a lambda over 4 sized elements and spacing, then we get this red curve here. So now we have lost a lot in the number of eigenvalues. We only have 1/4 of the number of eigenvalues, and some of them are large and most of them are small. And if we go down to lambda over 8 by lambda over 8, then we have even fewer. We get the number of non-zero eigenvalues by a factor 4 again, and many of them are 0. So channel sparsity always exist, even in anisotropic fading when we are considering IRS. And that is something that we should definitely utilize when we are designing future systems and try to learn the channels. There are two contributing factors: sub-wavelength sized antennas and a two-dimensional surface. And when we on top of this are adding spatial correlation or a distribution of multipaths that are non-isotropic, we will have even more sparsity. Okay, what about channel estimation then? The IRS configuration is complicated because the IRS is blind. It should be configured to reflect the signal towards the right location, but it can't estimate the signal itself. There are different solutions that people have been proposing. One is to have a fraction of active IRS elements. So you have a surface that is mainly reflecting signals, but a few of them can receive signals and estimate channels. And in that way, you can estimate what configuration to utilize and utilize a spatial correlation to do that. And this is definitely convenient, but I think it is the wrong way to go, because it sort of removes the whole low-cost argument. The idea that we should have a big surface with low cost because all of the components are being passive. If we have 1,000 elements, whereof say 1% is receiver antennas, then we have 10 antennas, and that is a large number, so it will definitely not be cheap. So I will more talk about solution 2 based on codebooks. And the idea is then that you have a, for example, user terminal that transmits a known signal over and over again, as you would do in order to learn the channels. But the important difference from a conventional system is that the IRS is changing its configuration over time. And in that way, we can get different measurements of the received signal with different configuration at the base station. It can solve some kind of optimization problem, like the ones we have described earlier, and then feed back the preferred configuration to the IRS controller. And in this way, we can figure out a good configuration. So let me show you how this might happen. And I will not utilize any sparsity or anything like this. I will just use it in the most basic form. So the received signal, set of n at time n, will be a transmitted signal multiplied with the channel that we described earlier, a direct path, and then a element-wise product between the channels to and from the surface, and then we have the configuration vector here, and then we add the noise. And say now that we are repeating the same signal L times. So to transmit the signal x of n is equal to s. And then let me call A times B here as a cascaded channel C, just for simplicity, so we don't need to repeat the same notation many times. And for each time I'm transmitting the same signal, I'm changing the configuration from omega theta 1 to omega theta L. In that case, the received signal will look like this, but I will be changing the configuration for each n. Let me gather all the received signal in a vector matrix like this, set 1 to set L. And then I'm transmitting the same signal the whole time, so same S multiply with HD. And then I just write 1, 1, 1, 1 here, because the configuration is always the same. There's always no real factor here in between. Then I have this C vector, and I take an inner product with a different configuration every time. So I write them here as the columns of a matrix. And then I multiply with S, which is the same signal every time, and then I have the noise here. Okay, I can now call this set, I can call this omega, and I call this W. These are then describing all of the signals that I'm having. And set, if I write it like this, how is the received signal obtained from S? Well, S is multiplied with this 1 here, and then HD, and S is also multiplied with this omega and C. I can write this in this form here. HD and C in the same vector on top of each other if I put this 1 here on top of the omega. If we multiply this together, we will get these terms again. And then we add a noise to it. So this is the received signal. And what I'm after is to learn a channel. What is the channel? It's HD and C. I'm not trying to estimate the individual A and B channel, because it's only the cascaded channel C that matters for us. So how can we figure out what would be the channel here? Well, we would like this matrix here, omega tilde with the ones on top of it, to be invertible. Because if it is invertible, I can multiply with the inverse of it from the left-hand side here. And then this matrix goes away and I instead get the inverse here. And then I multiply with the inverse of S, or just divide by S. And in that case, I get only this vector here with the channels on its own. And then I get some additive noise. And if I have a strong enough signal, then this additive noise will be weak, and this is a good channel estimate. In order to achieve that this matrix is invertible, I need to transmit a certain number of times. So in this case, I need L to be equal to n plus 1, because I have the number of rows that I'm having here is n. So we have n plus 1 different entries in this vector. So in order to achieve something that has 1 on the first row, and then it is in general a invertible matrix, we can, for example, use a DFT matrix, discrete Fourier transform matrix of dimension n plus 1. There is also something known as Hadamard matrices that can be utilized. But then we need n plus 1 to be a 2 to the power of something. This is the basic principle of channel estimation. Can we exploit channel sparsity somehow when we have received a signal like this? Well, as I was pointing out, C is probably having some sparsity, but exactly how we can improve the channel estimation to exploit that sparsity is still something that people are working on. And a year ago, I was pointing out in this paper, Reconfigurable Intelligent Surfaces, 3 myths and 2 critical questions. This was one of the critical questions. How can we do the channel estimation as efficiently as possible? And use sparse channel for that. Maybe group some elements together to simplify the estimation because of this. And that is particularly what we did in this paper with the experiments I was describing earlier. We had 20 rows and 55 columns, and each element could only have 2 states, plus or minus 90 degrees as phase shifts. How did we figure out how to phase shift? Well, we were considering a setup where we were having a dominant line of sight path. So we knew that a array response vector will take a signal coming in from one direction and shift it in one particular direction. And to figure out how to sweep the beam in different directions, we were doing like this. We were going through each row and we were flipping to opposite state and saw if we get better or worse SNR. If we got the better, we kept the configuration. If it was worse, we switched back. And then we took the next row and then the next one, and we repeated this over and over again. And when we were done with that, we took all the columns and did the same thing. So we are essentially sweeping around with beams horizontally and vertically in order to figure out in which direction we should reflect the beam in the best way. It's not an optimal way, but it worked in that experimental setup. All the channel modeling and IRS optimization that I have considered so far is for narrowband channels. But wideband channels are a practical use. Most channels in reality are wideband nowadays. And what is important with wideband channel is frequency selectivity. So here I'm showing different subcarriers, 1,000 different subcarriers, and what will happen if we are sending beams in different directions. What will be the path loss in those cases? And when we have a non-line of sight scenario with strong frequency selectivity, we will see these big variations. So different beam angles will provide us with different path loss at different subcarriers. Why is that? Well, a channel consists of many paths, each one with different phase shifts. And at different subcarriers, the phase shift will become different for these different scattering elements because of the wavelength has changed a little bit depending on what frequency we are considering. So for this reason, in 5G, for example, we are using digital beamforming so that we can transmit on each antenna a sum of many different beams, and we can change it for different subcarriers as well. So we can tune it over for every subcarrier, we can just select one or a multitude of beam directions and utilize them when transmitting. When it comes to line of sight scenarios, we often have one dominant direction and then we have some weak channels around it. so some weak frequency selectivity. So this is what I'm showing here. There is 1,000 different subcarriers, and depending on what beam direction we are transmitting in, we will get different path loss again. But we can see that there is one dominant direction here, namely angle 0, where we have a line of sight component. So we beamform there, we always, on every subcarrier, get this rather strong signal. And then there are variations around due to the multipaths. But this is the good solution. And this is something that is considered in millimeter wave 5G to use analog beamforming, where we know that we will only use this technology in line of sight scenarios, or scenarios with one strong path. And then we can lock onto that path by using phase shifters. And just send one angular beam in one particular direction that is the same on all the subcarriers. And here comes the important thing. This is essentially what an IRS is doing. It is phase shifting the signals before they get re-radiated. So it must be the same on all the subcarrier in a multicarrier in a wideband scenario, which means that we can expect that an IRS will be mostly effective in scenarios where analog beamforming would work well, when we have a low frequency selectivity in our channels. So let us extend the system model to an orthogonal frequency division multiplexing, or OFDM system model. We transmit from transmitter to the receiver once again, but now we have multiple distinct paths, A1 to ALH, and then we have multiple distinct paths from the elements to the receiver, B1 to BLG, and then we have the same phase shifts all the time. So what does it mean here? Well, it means that these different paths here are assumed to be received at different time instances. We are transmitting over a lot of bandwidth, we are sampling quickly, and therefore these paths are showing up at different times. So when we are determining our time domain end-to-end channel, there will be multiple taps on it. And we can compute it like this. We are taking, once again, the product between one of these distinct paths from transmitter to the IRS, and one of these ones from the IRS to the receiver. We sum over all of these paths, and for each L, 2, and I from, we take this element-wise product again, as before. And then each path is only showing up occasionally at certain time instances. So we take the corresponding delay to the surface and from the surface, which I, for simplicity here, assume that they are integers. So they are falling into just one of our many taps. And then we take a Kronecker delta function here, which is outputting 1 when these delays are sort of equal to 0 compared to the sampling time. So we are compensating for the first paths. So it should be 0 in that case. And then we have later paths where we take these numbers and we subtract 1, then subtract 2, up to m-1, which are the number of taps that we're having. So each combination of a path here and the combination of path here will show up in one of these different m taps. Okay, what would we do then to communicate over a channel like this? We would take it into the frequency domain. So if this is the end-to-end channel matrix with m taps, we are multiplying with the DFT matrix, or actually the truncated DFT matrix, with k rows and m columns. So k is the number of subcarrier, and that is larger, usually much larger than the number of taps. And then we take this matrix with the transpose on it just as before, and we multiply it with this configuration vector. And that will then give us the channel on each of the different subcarriers. So if there were only one subcarrier, then f would not really exist here, and we will only have one column here. So that will bring us back to what we had before. But now we have multiple taps and we have multiple subcarriers. What will then be the sum rate expression that we will get in a scenario like this? Well, the rate in megabit per second or bit per second that we have is that we take the bandwidth and we divide with the number of subcarriers that we have k, and then we, to deal with the number of taps we have in our channel, in OFDM we have a cyclic prefix of length m-1, so we need to divide by that as well. Then we sum up over all of our different subcarriers. For each one of them, we get a log 2 of 1 plus an SNR, which is the transmit power divided by the noise power multiplied with this factor that comes from the gain of the channel that we are getting. And if we replace this with what we had before, then we should have the omega that describes the configuration of IRS. We should have this channel matrix describing the channel from and to the IRS. And then we should have the F matrix, and for each of the subcarrier we just get one of the rows in this F matrix, the DFT matrix, like this. Okay, this is the sum rate expression, rate over all of the subcarriers. How do we select the configuration in this case? That is the difficult thing. Ideally, we would like to select a different configuration on each subcarrier. So as an upper bound, assume that we could do that. Well, in that case, we should select omega to match with this term here. And in similar way as before, we would get then to take this vector here and take it one norm and square it. Essentially the same thing as we did before. The problem is that we are not allowed to do that. We must have the same configuration on all of our K subcarrier, and K can be 1,000 different subcarriers. So how do we deal with that? Well, there are some early works on this, for example by Ru Chang in this paper here, where they were proposing the strongest path maximization, or STM method. This method is based on the idea of going through all of the taps in the V matrix, figuring out which one would have the largest one norm that is squared, because that is what we're showing up if we are transmitting only on that tap. And then we figure out that maximum index. We are then selecting the configuration to match with that tap. So the idea is that if one of these taps here is containing a strong signal, it probably comes from a line of sight or strongly reflect the signal, and then we should focus on that one because it will dominate over the entire frequency band. And here is an example of what can happen in that case. So we have a transmitter and a receiver, 200 meters apart. There's a non-line of sight channel between them. And then we have between transmitter and the IRS 200 meters as well, and it's either line of sight or non-line of sight. And then we have a 20 meter line of sight path to the receiver. So the receiver is in the vicinity of the IRS, which is 0.5 meter by 0.5 meter large. And this is a simulation from this recent paper that you see down here. And let us consider first when we have a line of sight channel between transmitter and receiver. So there is a direct path and then there are some scattered paths around it, but those ones are usually much weaker than the true line of sight path. Then what I'm showing here is the rate in megabits per second as I'm changing the bandwidth on my signal. And the upper bound, when I can configure my IRS individual for each subcarrier, is this red line here. If I'm instead optimizing the IRS based on this STM, the strongest path optimization, then we are getting this black curve. And it is rather close. There is small loss, but not very much. So we can almost get all of the power through the channel because there is a line of sight path that the IRS will focus on. As a reference, suppose that we are replacing the IRS with a metal sheet that is just reflecting the signals according to Snell's law. Then we get much smaller values here. So having this heterogeneous surface that we are tuning is really important in order for this to work out. If we are instead having a non-line of sight path between transmitter and receiver, so we are taking away the strong line of sight path and only keep the multipaths, then this is the result we're getting. We should notice that the rate values are much smaller, so everything is down here. And now the upper bound is a bit above the case with IRS, but not that much. And the optimized and the metal sheet case are almost on top of each other. So we are really not seeing any large benefit of having an IRS unless we have a line of sight path both to and from the surface to the receiver in wideband scenarios. So this is when the IRS is really effective. Here's the experimental validation of this. So it is from the same paper as the experimental result I was showing previously with the setup. And here is a transmitter 50 meters away. You can see what it contains. It is a transmit antenna, a horn antenna, directed in this direction. It is transmitted at 5.8 GHz using Wi-Fi over 20 MHz, and there is a particular transmit power. And when the signal is bouncing off a copper plate here, and is supposed to be measured at the receive antenna here, which is also a horn antenna directed towards the surface, then this is the measurement. Here you see the 5.8 GHz and the 20 MHz is 10 MHz per square here. And we can see there is some signal power measured here that is larger than the noise that we can measure in the adjacent band, but it's not much. If we are replacing, however, the metal plate with an IRS, and we are instead configuring it to beamform the signal towards the receive antenna here in a passive manner, then we get this result. Now the received signal over our 20 MHz goes up to minus 39 dBm compared to minus 66 before. So we have a 27 dB improvement in SNR thanks to the IRS. It's the same setup, but we are now having a heterogeneous surface here that is reflecting the signal towards the receiver. So this is really working out terrifically. So before I wrap up part 1, let me mention some of the competing technologies and potential weaknesses of the IRS technology. So passive repeaters is something that has been utilized for a long time to cover the countryside. When we have a base station somewhere, and we know that there are big objects that will shadow receivers here. For example, this is a valley. Then we can put up a metal plate like a billboard that has a line of sight to the transmitter, and that is directed so that it beamforms signals down to this area here. The good thing with the passive repeater is that it's fully passive. No power is needed. It's just a metal plate that we put up there. But there is no real flexibility. We need to select it large enough to collect energy, but not too large that it is sort of beamforming signals in a very narrow manner into this valley, but it should sort of cover the entire valley. And IRS is a smarter piece of equipment because it can take the signal from the transmitter and it can beamform it. Sometimes one user, sometimes another user. So we can get a stronger beamforming gain. We don't have to fill the entire valley at the same time, but we can configure ourselves depending on which user that is served at a time. But we must control it, and it requires some power to do that. And in general, this idea of having an element, an entity, in between a source and destination or transmitter or receiver that is helping out with controlling the environment was something that 10 years ago was known as cooperative communications. And some of the examples in the terminology or taxonomy that was used at that time is regenerative and transparent, or half duplex and full duplex. So regenerative cooperative communication technologies are such that they are receiving a signal from the source and then they're analyzing them and retransmit something. So one example is a decode and forward, or DF relay, that is receiving a signal, decode it, re-encodes it, and then transmits it again to destination. And it can either do this at different times. So at half duplex mode, they're first receiving and then transmits it again. Or there is also new full duplex technologies that are listening and transmitting at the same time. The other category are transparent cooperative communications. And this is when we are taking the same signal and retransmits it. It could be in half duplex mode, like an amplify and forward relay or a repeater that takes a signal here. They are not analyzing its content. It doesn't need to leave the physical layer. It just amplifies it and retransmits it. And then there is the full duplex mode, like the passive repeater I was just describing, or the IRS, which is also a kind of full duplex transparent relay or cooperative communication entity. So decode and forward relays are used in cellular technology of today. Amplifier and forward relays are old school analog repeaters that has been around for 100 years. And really the new emerging technologies are the full duplex relays and the IRS. So these are sort of the competing technologies that you should keep in mind when deciding on what kind of equipment to deploy in a real scenario to improve coverage. And I think it's not really one or the other. There are different choices that will be ideal for different situations. Another aspects to remember when it comes to the link budget that you can achieve in a system like this is that when you're having a transmitter that is sending a signal towards the IRS, that is then scattering the signal or reflecting it as a beam towards the receiver, then if there is other signals, interference or noise or whatever we would like to call it, that is impinging on the surface, those signals will also be scattered. And they might be scattered towards the receiver, but at least they will be scattered around. And what is important here? Well, it is that we are changing the environment in order to reflect signals more. So you think about it as painting a room with bright colors. It will feel like there is more light there because the signals, the light is not being absorbed, it's reflected. And in the same way, the interference that is reflected by the surface will be proportional to the size of it due to this aperture gain. There might not be a beamforming gain of the interference, but it will still be reflected, so it will be more interference around. And here is an example of how the IRS might actually reduce the sync-to-noise ratio. So the thing is that the SNR will contain one component which is the same as before. The transmit power, and then we have the square root of rho, the direct path, plus n times square root of alpha beta. That is what we have for the reflected paths. And then we should divide by the noise power, but also something I call electromagnetic interference, or EMI, which have a certain strength. This might be background radiations, or it might be interfering signals from other sources. And we multiply with n because we have n elements, so they are scattering the element, scattering this electromagnetic interference proportional to the size of the IRS. And suppose now, in the simulation I'll be running, that I have isotropic electromagnetic interference, so it comes in from all directions uniformly, and that the SNR of the EMI here, when it is reaching the surface, is that the signal of interest is 20 decibels stronger than the interference that is coming into this element. So supposedly it shouldn't make any difference, right? Well, here is an example that it can make a difference. So I'm showing the average SNR here over different randomness here of the EMI. And I have different number of elements per dimension in my square sized iris. So it's 10 by 10 or 20 by 20 or 30 by 30 and so on. And if I have a rather weak direct path, so we can essentially neglect that one, then what happens when n is increasing, number of elements? Well, then this path is increasing, the EMI part is increasing, and we will see that we get n square here and n here. So yeah, we are benefiting from having an IRS. And what we can see is that the black curve here is without EMI, then the signal SNR is growing quickly. But with an EMI, we are getting something that is growing much more slowly. Why? Well, because this term is also growing with the number of elements that we're having. And if there is no IRS at all, we get this curve here that is constant. So in this case, the IRS is still providing an SNR improvement, but it's a slower pace. However, if we have a rather strong, it's not that strong still, but we have a direct path that might be dominating over the reflected path for a while. Then, when we are increasing the number of elements and we have no EMI, we get a black curve that is increasing. If we have no IRS, we have a blue curve. But if we have an IRS and we have this EMI, we see that the SNR is actually going down as we add more elements. How can that be? Well, it's because the scaling here of n makes the additional EMI non-negligible, while the improvement in signal power is small. Even if we have a 20 decibel gain over the EMI, this part is strong enough to not see that difference. So an IRS can sometimes reduce the performance, even if we are configuring it in the right way, because of it reflecting noise interference from other sources. And the asymptotic SNR will, under the presence of EMI, grow as n and not n square, because we have n square here and we have n here, so when n grows, one of the n's are cancelling out each other. We only get the passive beamforming gain. So careful deployment is necessary when using this technology, and to utilize it mainly to improve the SNR in scenarios where the direct path is weak. So to summarize, what is the most promising example of using IRS? Well, I'm considering two dimensions, a strong direct path and a weak direct path. And the case when we have a non-line of sight to or from the IRS, or when we have line of sight both to and from the IRS. If we start with the non-line of sight case, then irrespective of if we have a strong or weak path, the IRS isn't effective, because it can only reflect signal from one direction towards one location. And if we have many paths, then it can only lock onto one of them, and the difference it will make is very small. And it also becomes rather difficult to estimate, because there is no real structure in the channel. However, if we have line of sight paths to and from the IRS, then it's interesting to talk about if we have a strong or weak path. If we have a strong direct path, then the IRS adds little to the direct path, unless the surface is very large. But if we have a weak direct path to the receiver from the transmitter, then that is the golden scenario here. We have large gains of having the IRS, and they hold even in OFDM scenario, because we can lock onto those line of sight paths. And there are rather few parameters to estimate, because we should estimate essentially an angle to the surface and from the surface, and figure out how to configure our phase shifts.